talked about work. Let's talk about power. Let's talk about potential energy.
Is this due next? I mean on Friday?
Yes, the retest is due on Friday.
October 30th. Woo!
Maybe sometimes it just likes to look fake.
Okay, does everybody understand the deal? Retest? The retest, the deal is that you work those two problems, you turn in on Friday, I'll take that grade, and I'll take your test grade, and I'll average. All right?
And if we don't want to, we just don't do it.
If you don't want to, you don't have to.
I'm gonna not give the extra 2 points.
I can get the extra 2 points. Okay. Andy, you're going to do it, right?
She already started.
Put it away. Don't start it. Put it away.
Oh wait.
All right. Power. Okay, last year power was... What the heck was power last year?
Work over time.
Okay, work over time, the rate at which work is done. Okay? Okay, what else was it last year?
FB.
Yes, we have an FB in there.
Because that was fun to do.
What else?
Change in kinetic
Math.
Yeah, change in energy over change in time, right? Okay, these three. Actually, change in kinetic, it could be change in any type of energy. So essentially, it's the change, it's the rate at which work is done or the rate at which energy is changing. Now, that's really the same thing, because remember that work is a change in energy, right? Accomplished by a force, right? Okay, so we're going to change this up just a little bit. You can still think of it as all those things, but power is dW dt. Now that's capital W, by the way, not omega. That's the rate change of work with time. Okay? Rate change of work with time. All right, so no big deal. What's our units on that again? That's joules per second. So you got a joule per second, which is a watt. Okay? So yet another W to deal with. Okay? So, change in work with change in time. Or dW dt. And, oh, very important, please, everyone. A lot of times, we know the power, but we want to know either energy or work. So don't forget that power times time is going to give us work, or it's going to give us how much our energy has changed. Okay? That comes in real handy. That's going to come in real handy, particularly when we get to electricity, because in electricity, particularly circuits, it's very easy to calculate power, but very difficult to calculate energy or work directly. So we calculate power, and then we just multiply by the time to figure out our work or energy. Okay? Turns out to be easier that way. All right. Was there anything else we wanted to do here? You want to do integrals?
Yeah.
Do I want to do an integral? I have one here.
Why do you take up like why do you take it with normal lines?
Let me look at that. We'll come back to that. We may do that integral. We may not. Because we need to start talking about potential energy. Okay, what we're going to talk about right now is going to be a little bit of a review, and then we're going to work backwards. Actually, what we're going to talk about now is going to be review from last year and really the year before as well. Potential energy. But then we're going to show where these things come from. Okay? How they were derived originally. Okay? So first of all, potential energy.
This is recycled paper.
Okay, potential energy. All right. What are the types of potential energy we've already talked about from last year?
Gravitational, spring, electrical,
Nuclear?
strong nuclear, kinetic.
Sort of. Okay, these big ones right here, gravitational,
I think we should get anti-force, just because. Because there's antimatter,
spring,
should be anti-force.
electric.
Anti-vectors.
Okay? All right, the equations for these are U sub G equals mgh, U sub S equals 1/2 kx squared, and U sub E equals, anyone remember this one?
Q.
K.
K, Q,
1, Q.
But we won't use that. Isn't that thermal?
K, Q1, Q2 over R, or if you prefer, if you're a purist, 1 over 4 pi epsilon naught, and we will be purists this year.
No, we have to be curious. No, I don't
Yes,
know
we
about
will.
that.
I'm going to show you where that 1 over 4 pi epsilon naught comes from. And not everything is 1 over 4 pi epsilon naught.
No.
Yes. Like for instance, if you have a point charge, then you'll have 1 over 4 pi epsilon naught. But if you have, say, like a line of charge,
Of course it's different.
like in a wire or something, you won't have 1 over 4 pi epsilon naught.
No.
And if you have a sheet of charge,
You'll definitely not have.
you won't have one either.
But are they like easy ones you can remember, or are they?
Yeah, this one's just epsilon naught. This one I don't remember off the top of my head. I think it's 1 over 2 pi epsilon naught. But I have to look it up. I don't remember off the top of my head.
How can the
Hang on,
charge?
2 pi. Yes. All right, so epsilon naught is the most basic. And we'll talk about that when we get there. All right, so here's the deal. All of these are a type of energy, but all of these, you don't have other types of energies like friction potential energy or normal potential energy or tension potential energy or any of these sorts of things, okay? And the reason why is because of the special, types of forces that these are related to, okay, called conservative forces, all right? So let's go back and take a look at that. All right, gravitational force is big G m1 m2 over r squared. We have spring potential, F sub G. F spring equals negative kx. And we have electric force equals K, Q1, Q2 over R squared. And already I'm being a bad boy. 1 over 4 pi. There we go.
So that's standard now.
Well, yes. Yes. All right, all of these have a function of position. Right here,
Yeah.
right here, and right here. Okay, other forces do not, like drag. Drag, which is BV to the n power, okay? Or force of friction, which is mu force normal, or normal force, or tension, or any of these other ones that some of these don't even have equations, at least at this point in our lives, okay? So if they don't have a function of location, then they will not be a potential energy associated with them, okay? It's as simple as that. So let's move straight on to, since we remember our potential energies from last year, how do we get potential energy? All right? Okay, so here we go. Let's say that this is you, and you're lifting this big barbell. Okay, you're lifting this big barbell, so,
It really didn't work, so you just keep it up.
all right, you go from there to
It didn't work, so you just keep it. You don't pull back.
I want to be that.
to here.
It's insane.
All right,
His wrist goes
Okay.
through his arm.
how much work have you done? Assuming this has a mass of
On
m
what?
and you've lifted it a distance h.
In
Okay, the work that's done by you is equal to F cross,
Dot.
F dot D. F dot X or R, I don't remember what it is on our equation sheet, I think it's R. But it's F R cosine theta, but for us it's going to be F D cosine theta. Actually FH, sorry. FH cosine theta. All right, what force do we have to apply to it to lift it? Mg. A force at least mg to lift the darn thing. So mg to lift it. Which way is your mg that you apply to it?
Directly opposite.
This way, right? You apply a force upward. This force is equal to mg to lift it, right? So that's mg up. H is up. Cosine theta is?
1.
Why 1?
180 is
It's in the same direction, so.
Because you're moving it that way and you're applying your force that way, so cosine of 0 is 1. So there you go, you get mgh. This is the work done by you. Work by YOU. Now, how much work is done by gravity during this?
negative.
Okay, the work done by gravity is equal to FD cosine theta, which is mgh times the cosine of 180, which is negative 1. So it's mgh negative. Okay? mgh negative. All right? So, the work done by gravity, okay, is equal to a negative change in the potential energy. Okay? Let me say that again. The work done by gravity is equal to a negative change in potential energy. All right? All right, so I'm going to make a general statement here. This is always true. The work done by a conservative force is equal to the negative change in potential energy that's associated with that conservative force. Okay? Sorry, all you young liberals. This is a conservative force.
You got it. You got that another thing. You got it.
All right. If you have a conservative force,
There's a liberal force that will oppose it. They're liberal established.
listen, if you have a conservative force, you can define a potential energy for it. Shh. Okay, if you have a force that is a function of location, you can define a potential energy for it. The work done by the conservative force will equal a decrease in the potential energy
Which makes sense. Like it's
of the system, okay? So like when the work done by gravity is positive, think about it for a second. Here you go. Is gravity doing positive work? Yes, but what's happening to the gravitational potential energy? It decreases. So when the work done by a conservative force is positive, the potential energy of that particular conservative force will decrease. And that's our statement right here. All right? Now, we can write it this way. Because work is equal to integral F dot dr equals negative change in potential energy. Okay? Got it. And there we go. Now, if you would prefer, you can write that a different way. There is a different way to write that. This is the integral form. Shh. This is the integral form. You can write this in differential form. If I write this in differential form, it'll look like this. By the way, I should write conservative force here. The conservative force is equal to negative du dr. The negative derivative of the potential energy function. Okay? So let's take a look at that real quick. Let's look at spring potential energy. Spring potential energy equals equals 1/2 kx squared. Sorry, 1/2 kx squared. Sorry, almost dropped it. Take the derivative of that with respect to r.
KX, negative KX.
Oh my goodness.
KX.
Negative kx. Hey, that's the spring force.
How'd you get negative?
Based on that equation.
All right.
We're amazed by the
Now,
simplicity.
hang on, quiet down, everybody. Okay, next time what we will do is we'll derive the gravitational potential energy equation. We'll derive the spring potential energy equation. And then we'll look at potential energy functions in general.